Good afternoon, everyone. Thank you for joining us again. Welcome back. I'm Steve.
And I'm Scott.
Together, we're Backyard Musings, broadcasting live Apple Valley, California.
Science and Technology Channel.
So back last year, we talked about new stuff for batteries, solid state batteries, all kinds of materials. MIT researchers have developed a revolutionary sodium air fuel cell.
This is fascinating.
Yeah.
If this is the real deal, this could be game changing.
So
right
it's
right?
not a battery. It's like it depletes and then it can be refilled up, right? It's a fuel cell that can replace heavy lithium-ion batteries in aviation, rail, and marine transport. Using liquid sodium and ambient air, this system offers triple the energy density of current EV batteries, potentially enabling electric aircraft. The cell emits no carbon dioxide and even captures CO2 from the air, producing baking soda as a byproduct. I've got baking soda in the refrigerator.
Hey, there you go. Yeah. Use baking soda for all kinds of things.
Bake with it, too. The findings were published on the 27th of May, 2025. It's like last week in Joule. Would you like to know more?
Traditional batteries are starting to hit their limit when it comes to how much energy they can store for their weight. That's a big roadblock for the future of electric transportation, especially for high energy hungry machines like airplanes, trains, and ships.
Mm-hmm.
Now, a team of researchers at MIT and their collaborators may have found a way around it, and it's exciting. I don't know if it's exciting, but it's pretty cool. Yeah.
Instead of a battery, their new design is a fuel cell. Like a battery, it generates electricity through chemical reactions, but there's a major advantage. It can be refueled quickly rather than slowly recharged. This particular fuel cell uses liquid sodium metal. Isn't that what the T-1000, Terminator T-1000 was made out of?
Didn't see the movie, sorry.
Okay. Liquid sodium metal, a low-cost and widely available material, as its energy source. The other ingredient? Ordinary air. A solid ceramic layer between them helps sodium ions move through, while a special electrode on the air side sparks a reaction that produces electricity.
So if this thing comes to fruition, right? That's a term.
Yeah.
This could do away with the issues with lithium batteries, could it not? I mean, on a large scale, I'm talking about like for cars.
First and foremost, the weight.
Correct, and the people that are
distance.
The people that are trying to put a monopoly on that, right? Mainly our friends, the CCPers, right?
Yeah.
And yeah, I mean, I'm not trying to take away from the people that are trying to make money on lithium and the people that are mining it and stuff, but this is
imagine it on airplanes.
This is cool, right?
Yeah.
So this could change the game for, like we were saying, like transportation of goods in trucks, because the issue there has always been the weight of the batteries, right? You need so many huge batteries
and range,
right?
Yeah,
and time to recharge and all that kind of stuff, right?
Yeah.
When the team tested a prototype, the results were striking. The sodium air fuel cells stored more than 3 times as much energy per kilogram as the lithium-ion batteries used in today's electric vehicles. That's a massive leap forward. The findings come from MIT doctoral students Karen Sugano, Sunil Mayer, Sahir Ganti Agrawal, Professor Yet Ming Chiang, and colleagues.
These are students.
Yeah, except for Professor.
Oh yeah.
Ming, but yeah, this is cool. This is cool stuff. I mean, MIT, they're known for attracting the best of the best,
smart,
right?
Yeah. Quote, we expect people to think that this is a totally crazy idea, says Chang, who is the Kyocera professor of ceramics. I didn't know there was a professor of ceramics. He continues, if they didn't, I'd be a bit disappointed, because if people don't think something is totally crazy at first, it probably isn't going to be that revolutionary.
And I'll bet that ceramic school they're not making ashtrays and cups and mugs and that kind of stuff. This is
cutting edge stuff.
Serious stuff, yeah. And this technology does appear to have the potential to be quite revolutionary, he suggests, in particular for aviation, where weight is especially crucial. Such an improvement in energy density could be the breakthrough that finally makes electrically powered flight practical at significant scale.
Boy,
So,
Bernie
cool.
Sanders would love this. John Kerry would love this, right? They jet around everywhere.
Yeah. Huh. Then they wouldn't be able to get their carbon offsets, don't they?
Right.
Don't they?
Right.
Yeah.
Well,
whatever.
They'll deal with that when they get to it.
Yeah.
Quote, the threshold that you really need for realistic electric aviation is about 1,000 watt hours per kilogram, Chang says. Today's electric vehicle lithium-ion batteries top out at about 300 watt hours per kilogram. Nowhere near what's needed even at 1,000 watt hours per kilogram, he says. That wouldn't be enough to enable transcontinental or transatlantic flights.
Okay. So we start on a smaller scale, right?
Yeah, like regional hubs, Phoenix to LA.
Yeah. That's still beyond reach for any known battery chemistry. But Chiang says that getting to 1,000 watts per kilogram would be an enabling technology for regional electric aviation, okay, which accounts for about 80% domestic flights and 30% of the emissions from aviation. The technology could be an enabler for other sectors as well, including marine and rail transportation. Quote, they all require very high energy density and they all require low costs, he says. And that's what attracted us to sodium metal. Cool.
I don't know if you could use it in rail if it's practical, because those locomotives are heavy. They need horsepower to move.
Probably have to have a couple of them that would just be battery carriers, right?
I guess
to fuel
like in the old days, the wood carriers, where they throw the wood into the fire to stoke it.
That was old steam engines.
Yeah.
So, but I mean, you think about, this is kind of a crazy scale to look at, but like little electric trains you play with as a kid, those are all electric.
Yeah.
And there's electric trams and stuff in cities, or there used to be. I don't know if there still is, but where they have the cable, sticking up from the car up onto the power up on the cable. But BNSF,
they're hauling thousands of tons of materials. These locomotives.
Yeah, and sometimes they've got pull trains, and sometimes they've got push trains. And both push trains. So engines, and but yeah, I could see this. Just add a couple extra cars that are just batteries, and then you get to a stopping point, a freight yard or whatever, drop off those batteries, get new batteries that on your way. You don't even have to charge them. They're already charged and ready to go, or they're already fueled up or whatever.
Yeah, it's the fuel cells.
Yeah, already ready to go.
Sodium, whatever.
Sodium metal. Yeah, all ready to go. So,
okay, a great deal of research has gone into developing lithium air or sodium air batteries over the last 3 decades, but it's been hard to make them fully rechargeable. Quote, people have been aware of the energy density you could get with metal air batteries for a very long time, and it's been hugely attractive, but it's just never been realized in practice, Chang says.
By using the same basic electrochemical concept, only making it a fuel cell instead of a battery, the researchers were able to get the advantages of high energy density in a practical form. Unlike a battery, whose materials are assembled once and sealed in a container, with a fuel cell, the energy carrying materials go in and out. So you'd have to a lot of maintenance probably, right? But still,
you have to be checking it, refill it.
Yeah.
The team produced 2 different versions of a lab scale prototype of the system. In one, called an H-cell, 2 vertical glass tubes were connected by a tube across the middle, which contains a solid ceramic electrolyte material and a porous air electrode. Liquid sodium, picture this in your mind, liquid sodium metal fills the tube on one side and air flows through the other, providing the oxygen for an electrochemical reaction at the center, which ends up gradually consuming the sodium fuel. The other prototype uses a horizontal design, so that was vertical, a horizontal design with a tray of the electrolyte material holding the liquid sodium fuel. The porous air electrode, which facilitates the reaction, is affixed to the bottom of the tray.
Tests using an air stream with a carefully controlled humidity level produced a level of more than 1,500 watt hours per kilogram at the level of an additional individual stack. Okay, so that would translate to over 1,000 watt hours at the fuel system levels, Chang says. Okay, well then they're They're getting there.
They're
right?
getting there, yeah. The researchers envisioned that to use the system in an aircraft, fuel packs containing stacks of cells like racks of food trays in a cafeteria would be inserted into the fuel cells. I can just imagine this, someone walking over with the thing, you know, and opens it up, takes the one out, and puts the other in, you know.
Yeah, locks it in there.
Yeah. Will be inserted in the fuel cells. The sodium metal inside these packs gets chemically transformed as it provides the power. A stream of its chemical byproduct is given off, and in the case of aircraft, this will be emitted out the back, not unlike the exhaust from a jet engine.
Okay. But there's a very big difference. There would be no carbon dioxide emissions. Instead, the emissions consisting of sodium oxide would actually soak up carbon dioxide from the atmosphere. This compound would quickly combine with moisture in the air to make sodium hydroxide, a material commonly used as a drain cleaner, which readily combines with carbon dioxide to form a solid material, sodium carbonate, which in turn forms sodium bicarbonate, otherwise known as baking soda.
Yeah,
but we probably all have in our kitchens.
This is not going to happen at the rear of the plane. I mean, the only thing that's going to happen is that emission that's going to soak up CO2, right?
Right.
But they're saying you can do it, you know, in a lab, you can do all this and make your baking soda. So I'm wondering, is it going to take, trees need CO2, right? They soak up CO2, right? Is this going to adversely affect trees?
I don't know.
If it's on a large scale. I don't know.
Maybe they should try it flying over the ocean first. Not too many trees over the ocean, right?
Well, that's true. That's or Antarctica or the North Pole.
Right. Yeah. Or flying around in Egypt where there's not many trees.
Yeah, keep them away from the equator, right?
Just give it a try for a while, or do a little test.
Hmm.
Maybe they have
Put them in Egypt.
Test trees that they could use instead of like test mice. They could use test trees. I don't know, but I'm sure that the EPA, well, of course the EPA is going to be going away, but I'm sure the environmentalists are going to have their heyday
Cry
with this.
foul.
Yeah, and they're gonna, you know, they'll put it through the ringer. So hopefully it'll work out.
Yeah, it's promising. Let's watch this. What do you say we watch this?
If you've ever walked by a railroad track currently and seen all the junk that's along the side of the rails and the tracks from the diesel engines, because that diesel is it's a dirty fuel.
Yeah, you gotta admit that.
Yeah, I mean it's good fuel. And it serves its purpose, but it's dirty. So it would be good for the environment, I think.
Yeah.
You know, but anyway, good one.
All right, thanks, folks. Thanks for joining us.
Take care, everyone. Thanks.